In the last class, we discussed Schrodinger's time-dependent wave equation. Now let's look at Schrodinger's time-independent wave equation. The time-independent wave equation is the partial differential equation that is satisfied by energy eigenfunctions. Okay, so as before, let's consider an operator that commutes with the Hamiltonian. They will have a complete set of simultaneous eigenkets. So we'll write the eigenvalue equations as A acting on ket A prime is equal to A prime multiplied by ket A prime. This is for operator A. But these ket A prime are also eigenkets of Hamiltonian. So we can write H acting on ket A prime is equal to E A prime multiplied by ket A prime. So we have seen these things. Okay. Now let's say that the initial state of a system at time t0 equal to 0. Right. Let's say that at time t0 equal to 0, the initial state is given by ket A prime. Right. So initially it's in an energy eigenket, or these are called stationary states. Okay. Now we can find the state at a later time ket A prime t0 equal to 0 at time t. Right. This is the initial ket. This is the ket at a later time. Now we know how to obtain this. These are obtained by the action of the time evolution operator, which is minus I h t divided by h bar acting on ket A prime. Okay, the initial state. All right. Now this is the Hamiltonian operator, and this ket A prime is already an eigenket of the Hamiltonian. Right. So this equation now becomes ket A prime t0 equal to 0 at time t is equal to e raised to minus I e A prime t by h bar multiplied by ket A prime. All right. So these are the energy eigenkets. Now we can look at the position space representation of this. Right. So we just push a bra x prime from the left. Okay. So we can write bra x vector prime ket A prime t0 equal to 0 at time t is equal to. This is a number. So this bra will bypass this e raised to minus I e A prime t by h bar, and we will have bra x vector prime ket A prime. All right. So that's the equation that we have here. Okay, so this is the wave function called as the energy eigenfunction. Right, this is the position space representation of an energy eigenket, and it's a function of position. Right, this is called an energy eigenfunction. All right, so we say that this equation says that the energy eigenfunction at a later time t is equal to the initial energy eigenfunction, which is bra x vector prime ket A prime. Right, the initial energy eigenfunction multiplied by this phase factor exponential minus I e A prime t by h bar. All right. Now it is understood that initially the system is prepared in a simultaneous eigenstate of A and H with eigenvalues A prime and E A prime respectively, just as we mentioned in the beginning. Okay. So this is how the energy eigenfunction at a time t is related to the energy eigenfunction at time t equal to 0. All right. So the energy eigenfunction at time t equal to 0 is simply multiplied by a phase factor to get the energy eigenfunction at a later time. This is how the energy eigenfunction evolves. All right. Now let's substitute this into the time-dependent Schrodinger equation. So if you want to write the time-dependent Schrodinger equation for this wave function, it would look like this. Let me write it here. IH bar partial derivative with respect to time of bra x vector prime ket A prime comma t0 equal to 0 at time t. Okay, this is equal to, let me write as minus h bar square divided by 2m del vector prime square, all right, acting on again bra x vector prime ket A prime comma t0 equal to 0 at time t. There's also one more term, which is v of x vector prime acting on bra x vector prime ket A prime comma t0 equal to 0 at time t. Right? So this is nothing but the Schrodinger equation that we derived earlier. We are just writing the Schrodinger equation for this particular wave function. All right? But this particular wave function is special. This is an energy eigenfunction, and we know it's related to the initial energy eigenfunction in this manner. So we can substitute from equation 1. All right? So instead of this bra x vector prime get A prime t0 equal to 0 at time t, we can put this equation in. Okay? So this becomes I h bar partial derivative with respect to time of bra x vector prime ket A prime e raised to minus I e A prime t by h bar. All right. So that's the first term here. And on the right hand side, this becomes minus h bar square divided by 2m del vector prime square, and we have got bra x vector prime get a prime, right? Then e raised to minus I e a prime t by h bar. It's just this term, right? Plus v of x vector prime, again bra x vector prime get a prime, again the same term, minus I e a prime t by h bar. Okay. Now we have to take a time derivative here. This get a prime is the state at the time t0 equal to 0. So that's a get which is fixed at t0 equal to 0. All right. And the eigenbars, these are the position eigenbars which are used as bases, and base gets and base bars do not depend on time. This is a fact which we have already used. Okay. So a time derivative here acts only on this term. Right. And what do we get? This is ih bar bra x vector prime get a prime, and then partial derivative of this thing. What's the partial derivative of this thing? It is minus I e a prime divided by h bar multiplied by e raised to minus I e a prime t by h bar. Okay, we have just taken the derivative with respect to time, right? And on the right hand side we have minus h bar square divided by 2m del vector prime square acting on bra x vector prime get a prime. All right. Now this term does not have any spatial dependence, so we can simply write this as minus I e a prime t by h bar plus, again here v of x vector prime bra x vector prime get a prime. Okay, and e raised to minus I e a prime t by h bar. We see that this e raised to minus I e a prime t by h bar is everywhere, so we can just cancel them off, and we are left with this equation. Okay. Now here we have got an IH bar and there's a minus IEA prime by H bar. This H bar cancel. I multiplied by minus I becomes 1. And here this left hand side is simply EA prime bra x vector prime get A prime. Okay. And this side is just the same thing. Alright. Minus H bar. So let me write it again. This equal to minus H bar square by 2m del vector prime square bra x vector prime get A prime plus v of x vector prime, and we have got bra x vector prime get A prime, right? So we have got this equation. That's equation written here, all right? So we have got minus h bar square divided by 2m del prime square acting on bra x vector prime get A prime, that term is written here, all right? Plus v of x vector prime bra x vector prime get A prime, this term, this is equal to EA prime multiplied by bra x vector prime get A prime. Alright. Now this partial differential equation is satisfied by the energy eigenfunction bra x vector prime get A prime. Right. So this is the equation, the partial differential equation that is satisfied by the energy eigenfunction. Alright. Now a point to note is that in wave mechanics, the Hamiltonian operator is given as a function of x vector and p vector, right, as we have already done. So it is actually not necessary to refer explicitly to another observable A that commutes with the Hamiltonian, right? Because we can always choose A to be that function of observables x vector and p vector which coincides with H itself, right? So we don't need a separate A and H. We can directly take the Hamiltonian operator itself because it's already written in the written as a function of x vector and p vector. Right? So instead of A, we can take H itself. Okay. So we don't have to specifically refer to this eigenvalue A prime. Right? And we had this equation. Let me write this equation here again. This equation was minus h bar square divided by 2m del vector prime square acting on bra x vector prime get A prime is equal to, plus v of x vector prime bra x vector prime get A prime, this is equal to E A prime multiplied by bra x vector prime get A prime, right? So we don't have to now specifically refer to the eigenvalue of another operator A. Okay, so we can drop this and we can denote this eigenfunction as simply UE of x vector prime. UE of x vector prime. Okay, now if you do that, this equation becomes minus h bar square divided by 2m del prime square of ue of x vector prime plus v of x vector prime multiplied by, this is again ue of x vector prime, this is equal to e multiplied by ue of x vector prime. Okay, we have got the energy eigenvalue equation. Now this is the time independent wave equation of Schrodinger, announced in the first of 4 monumental papers written in the first half of 1926, and this laid the foundations of wave mechanics. Okay, in the same paper, Schrodinger actually applied this to the hydrogen atom and derived the energy spectrum. Right? Energy spectrum means the energy eigenvalues. All right. So this time independent wave equation is actually an energy eigenvalue equation. Energy eigenvalue equation. Right? We have got a differential operator this time acting on a wave function ue of x vector prime, which gives you a number multiplied by the same wave function. Right? This is an eigenvalue problem. So what Schrodinger did was that he solved this eigenvalue problem for a particular Hamiltonian. Right? And solving this eigenvalue problem means finding the eigenvalues and the eigenfunctions. And what are these eigenvalues? These eigenvalues are the energies. Right? So that's how he obtained the energy spectrum of the hydrogen atom. Now to solve this equation, of course, some boundary condition has to be imposed. Right? Now suppose we are looking for a solution with E less than V of x vector prime in the limit modulus x vector prime tends to infinity. So when we say that modulus x vector prime tends to infinity, we are taking both these cases. X vector prime tends to infinity in the positive x direction and x vector prime tends to minus infinity in the negative x direction, in the negative direction. All right. Now this means that the inequality relation is to hold for modulus x vector prime tends to infinity in any direction. Alright. Now the appropriate boundary condition to be used in this case, suppose we are talking about a case like this, and then the appropriate boundary condition is ue of x vector prime tends to 0 as modulus of x vector prime tends to infinity. Okay. Now physically this condition that ue of x vector prime goes to 0 in the limit modulus x vector prime tends to infinity. Alright, so the wave function, this is the wave function. The wave function has to go to 0 in the limit x vector prime tends to infinity. Alright, now physically this means that the particle is bound or confined within a finite region of space. Okay, this is understandable because this ue of x vector prime is a wave function of the system. Alright, so we have this interpretation. The modulus square is related to the probability density. Right, so if you add up all the probabilities over the entire space, which is given by integral d cube x prime ue of x vector prime modulus squared. All right, this should give me 1. This should give me 1. Now if this has to be 1, this is the normalization condition. Right, now this will be equal to 1. This will converge to 1 only if this wave function goes to 0 at infinite distances. Right, in other words, the particle is bound or confined within a finite region of space. Right, it's not spread out over infinity. It's confined within a finite region of space. All right. Now from the theory of partial differential equations, it's known that this equation, subject to a boundary condition, as we discussed right now, right, it allows non-trivial solutions only for a discrete set of values of E. Okay. Now if I take this partial differential equation and I try to solve it with the boundary conditions that we mentioned, with the boundary conditions that ue of x vector prime has to go to 0 at infinite distances. All right. Now with this boundary condition, if we solve this equation, the theory of partial differential equation says that we'll get non-trivial solutions only for a discrete set of values of E, which means that with this boundary conditions, this equation is going to be satisfied only for certain values of E. This is not going to be satisfied for any value of E. This is going to be satisfied only for certain discrete values of E if we impose the boundary condition that we just mentioned. Right, now this is something that's known from the theory of partial differential equations. And even if we don't know this, when we start solving the time independent Schrodinger equation, we'll actually see that the partial differential equation or the energy eigenvalue equation has solutions only for certain values of energy. If we are talking about a bound state, if we are talking about a system that's bound to a finite region of space, we'll always see that the solutions are obtained for a discrete set of values of E. All right. Now it is in this sense that the time-independent Schrodinger equation yields the quantization of energy levels. So this is famously called the quantization of energy levels, or energies are quantized. If you are talking about a confined system, we always find that the system can take only a discrete set of energies. It cannot have any energy it likes. It can take only a discrete set of energies. All right, this is called the quantization of energy levels. So energy is not continuous as believed in the case of classical mechanics. All right, so this is the case for a bound state. If you are talking about the energy of bound states, we'll always see that the energy is discrete. Okay. Now, once we write the partial differential equation, the problem of finding the energy levels of microscopic physical systems is a straightforward problem. All right, it's just a matter of solving a differential equation given certain boundary conditions. All right, so once we write the partial differential equation, we just use the techniques that we are already familiar with and solve this partial differential equation to find the eigenvalues and eigenfunctions. All right, this problem is straightforward. Right, some problems are more difficult than the others. Some problems may not admit exact solutions for the wave functions, etc. Right, but there are methods to attack the problem, right, to solve these partial differential equations. Okay. Now you might have seen similar problems as finding the characteristic frequencies of vibrating strings or membranes, etc. All right, we might have seen these things. Right, in all these cases, we just solve a boundary value problem. Okay, we'll take a quick look at history before concluding. All right, now this fact that exactly soluble eigenvalue problems, okay, eigenvalue problem as a partial differential equation, right, something like this, the differential operator u acting on u e of x, the partial differential equation acting on u e of x vector prime is equal to e multiplied by u e of x vector prime. All right, this is a partial differential equation, an eigenvalue equation which we need to solve. All right, it was already known to mathematicians that these equations can be solved using matrix methods, because in matrices also we have these eigenvalue equations. Okay, all right. And yet, right, it was not clear to the physicists at the time. Okay, we had matrix mechanics in 1925 and wave mechanics came later. Right? So when Heisenberg came up with his matrix mechanics, which essentially involved solving eigenvalue equations, right, it did not occur to the theoretical physicists that this can be reformulated using partial differential equations. All right. So if someone was sufficiently mathematically informed at the time, they could have immediately written down the same things in the language of partial differential equations. All right, but this is not how it happened. Heisenberg actually, no, sorry, Schrodinger actually came to this wave mechanics. All right, this partial differential equation, this eigenvalue equation independently. He did not start with matrix mechanics and try to write it in terms of partial differential equations. He came to this Schrodinger equation in a completely different way. Okay. So a close inspection of Schrodinger's paper shows that he was not at all influenced by the earlier works of Heisenberg, Born, and Jordan. So he did not start with matrix mechanics and try to write it in terms of partial differential equations, even though that was possible. People knew that it was possible at that time. All right. Instead, the reasoning that led Schrodinger to formulate wave mechanics has its roots in Hamilton's analogy between optics and mechanics, all right, and the particle wave hypothesis of Louis de Broglie. So Louis de Broglie had come up with this particle wave hypothesis. So Schrodinger was trying to obtain an equation that describes, that governs this particle wave. All right, so that's how historically he came to this Schrodinger equation. All right. Now, once wave mechanics was formulated, many people, including Schrodinger himself, actually showed the equivalence between wave mechanics and matrix mechanics. So it was shown that they give the same results and they are equivalent in the sense that it's the same thing written in two different languages, one using matrices and the other one in the language of partial differential equations. Okay. With that, let's conclude our discussion of time-independent Schrodinger equation. As we saw, the time-independent Schrodinger equation is nothing but an energy eigenvalue equation. It's an energy eigenvalue equation written in the language of partial differential equations. Partial differential equations. All right. Now, once we write it in terms of partial differential equations, it's immediately clear from the theory of partial differential equations that for bound states, right, for bound states or for certain boundary conditions, these partial differential equations can be solved only for a discrete set of eigenvalues. Okay, not for all eigenvalues, but only for a discrete set of eigenvalues. Okay. In other words, the energy levels of a quantized system, so the energy levels of a bound system are quantized, are discrete. Okay. All right. So we'll stop with that. Thank you.